Hello, everyone, and welcome to another wonderful day of physical chemistry. So, today we're going to continue our conversation on rotational spectroscopy, except for now we're going to move beyond a simple linear or spherical rotor and talk a little bit more in detail about symmetric rotors. So, symmetric rotors, despite their name, are not completely symmetric. Their distinguishing feature is that they've got two different types of moments of inertia. So they've got one dominant moment of inertia, which we're going to call the parallel moment of inertia, which by convention we typically represent being in the z direction, and then two perpendicular moments of inertia, which should be identical. And it's this fact that the perpendicular moments of inertia are identical is what constitutes this system being symmetric, because it's very easy to imagine, like in this case of an octahedral rotor, if I switch one of these atoms, all three of my moments of inertia would be very different. And this is an asymmetric system, and it's very hard to describe. So this will walk our way towards seeing cognitively where more complicated rotors will take us and what major trends we should be looking for. However, one of the benefits of a symmetric system is while they are much more messy than a spherical or linear rotor, they do actually have a couple of tricks that we can use. And again, we can imagine these as any number of structures, whether it's a modified octahedral structure or tetrahedral. So using these uh, general structures, we can use our classic energy equation, where we can constitute the energy as being the sum of each of the individual, the square of each of the individual angular momentums over the corresponding moment of inertia. And again, by convention, we're putting the parallel moment of inertia along the z-axis. And that leaves the x and y angular momenta to be paired with the perpendicular moments of inertia. Now, one of the things that is worth noting is that it's going to be very unfortunate if we try and use x and y angular momenta, because don't forget, these form a complementary operator set with each other as well as with z. So we're going to want to get away from this notation as fast as we can. And it turns out one of the easiest ways we can do this is by realizing that the sum of x and y is also going to be the difference in between the total angular momenta and the angular momenta in the z direction. And it is worth remembering that these do not form a complementary set. These operators are going to have a commutator that is zero. So these are commuting operators, which helps keep our math a lot easier. However, this does give us a slightly odd structure, as now instead of the single term in terms of the total angular momenta, which I had for a spherical rotor, now I've got uh, a rotation that's dependent on the total angular momentum, but also the angular momentum in the z direction, as well as the angular momentum in the z direction. One of the other ways we can imagine looking at this equation is really what I'm doing is I'm treating the whole system of, what if my whole system operated like a spherical rotor with with a moment of inertia of that in the perpendicular direction. But since not all of it has the same uh, moment of inertia, I'm going to subtract out the z direction and add it back in with the correct moment of inertia. This is a classic substitution trick that physicists really love to make use of. And that's kind of, to an extent, what we can how we can treat it. Because then we can isolate our total angular momenta term on its own, and then bring together these two angular momenta in the z directions together with essentially a prefactor that will relate the difference of 1 over the corresponding moment of inertia. So again, one way you can think about it, I'm replacing a certain amount of the perpendicular moment of inertia with the parallel moment of inertia. Now, because we are now solidly into spectroscopy and not just quantum mechanics, we can also express this energy in terms of in terms of wave numbers, as well as in terms of a new set of quantum numbers. So we have our classic set of quantum number of J, and this is going to correspond to the same thing as it always did, total angular momenta, and this will and this term essentially is the same as we found with the parallel system, where again we have our rotational constant representing the moment of inertia in the perpendicular direction. However, we are also replacing a certain amount of that B moment of inertia with our new moment of inertia in the parallel direction. And the extent of how much of it I replace is going to be given by K, where K can be thought of as the extent of movement in this parallel direction. So where our total angular momentum and movement is going to be the same as ever. It's going to go from 0 to whatever our current energy state is, as this is our dominant mode of movement. We're also going to be adding in this value of K. And it has possible values from negative J to positive J. So this helps indicate that K is giving us a certain extent of how much of the movement is happening in this happening in this parallel direction, and it can occur in a negative direction or in a positive direction. So we get this directionality in this K term. Now, one of the things I like to start with is let's take the simplest case. If K is 0, so if K is 0, what this means is that all of the rotation occurs in the perpendicular axis. So I've got no rotation about that principal axis. So let's go ahead and take a look at, this odd modified form of our symmetric octahedral system. So this is my principal axis. So any rotation in the parallel direction can be thought of this system as tumbling over, as rolling along over this axis. So essentially, we can model this almost like a sphere. If I have movement along this K direction, I'm essentially tumbling, or I'm essentially rolling. If K is 0, this means I'm not rolling at all. And the only sort of motion I have is this tumbling motion, where I'm essentially moving this, where these C atoms are moving to some extent. They are not staying still. So it's worth noting that this is going to be fairly similar to a linear rotor. So if all of my movement is essentially tumbling with the C, this is essentially the same thing as having a linear rotor. I've got no rolling action. I'm just simply tumbling. Now, one of the reasons why this is allowable is I'm not saying which direction I'm tumbling in. I could be tumbling along this axis. I could be tumbling along a slightly different axis. So we can imagine the C atoms going along this rotation, but they could also be tumbling along the angle exactly 90 degrees. And this is what allows us to still get that tumbling and rotation action while preserving the complementary nature of our angular momentum operators. So K equals 0. Essentially, I act like a linear rotor, and lo and behold, what we find is that my energy function is exactly that of a linear rotor, where again, beta term now just represent my B rotational constant simply represents the same exact thing it did when dealing with a linear rotor. However, if K is not equal to 0, so let's say that K equals J, what this then indicates is that most of my motion is accompanying from this rolling motion. So most of the axis is essentially these A atoms moving, but there is going to be a certain extent of wobble. Again, have to deal with the fact angular momentum is a symmetric operator. And in truth, what we have is some extent in between. And we can also see this because when K equals J, what I will have done is I will have subtracted out most of the influence of this first term, but not all of it. because this isn't just j squared, it's j times j plus 1. So I'll always leave a term of j remaining. There will always be a little bit that won't be canceled out. And one of the other important implications of what this means in terms of degeneracy of energy levels is, so again, if k is equal to 0, the degeneracy will be the same as it was for a linear rotor, 2j plus 1. However, if k is not equal to 0, what we have is 2 times that degeneracy. And one of the ways we can think about is we separated out our energy levels, so we aren't at a simple 2j plus 1 squared, but k could essentially be positive or negative. I don't know the extent of the rotation direction about the k-axis. And because of that, I'm going to have the same energy level, but I've doubled it because of some uncertainty about how much movement is occurring in that parallel direction. So yes, this gets a little bit messy. If you need to, try and sit around, dance, throw out your arms, and you can hopefully try and mimic some of these movements. Now, one of the other big things I want to clear up is one common point of confusion about what k means. So k is going to be indicating the direction of rotation with respect to the axis of motion. So if k is 0, I'm essentially just having a tumbling action. K equals j, I'm mostly a rolling action. This is not going to be the same thing as m sub j. So m sub j is also telling us a lot about the direction in which motion is occurring. But m sub j indicates the rotation with respect to an external source. So I have some detector that I'm going to call in the z direction. And then I'm going to be seeing how much of that motion occurs into the z direction. So let's look at essentially 3 cases where k equals 0. So we can have most of that angular momentum happening in the z-axis, at which point m sub j equals j. Okay, we've seen this before. But it's also entirely possible for most of this rotation, while it's still a tumbling action, to be pointed away from the detector in the x direction, the x or y direction. And we can even get to the point where it's tumbling end over end, but none of it angular momentum is pointed in the line of the detector, so I have an m sub j of 0. So this is kind of an important but subtle distinction. K is going to be with respect to the internal reference, so the center of the atom. How am I moving about that? Whereas m sub j really tends to tell me a lot about how I'm moving with respect to a detector. Now, with all of this information, it is worth noting we have one other big a big caveat we should acknowledge. And this is essentially that at high rotational speeds, rigid rotor starts failing me. And it starts failing me in kind of a significant way. Because as the system goes faster and faster and faster, those bonds are going to stretch out. And this stretching out is going to essentially slow down the rotation because I'm changing my moment of inertia. Because as r gets longer, moment of inertia goes up, modified the energy of the system, and even the speed of rotation. So again, the classic analogy of this is an ice skater. You go ahead and slow yourself down by putting your arms out. It's the same thing where we get the high speeds, we stretch out, and that kind of has this dampening effect. And because of this, we need to acknowledge what's called a distortion effect. And so what will end up happening is at high values of j, we're going to lower the energy level according to our general equation, where here, let's assume we're dealing with a spherical or simple system. So E j plus times j plus j1. This is my classic spherical or linear system, and I'm dampening it by the distortion factor of d sub j. And this is going to be essentially related to a ratio of my rotational constant and my vibrational constant. So you can imagine if I have a large uh, rotational constant. This means I have a certain degree of fast rotation, so or a large moment of inertia, so this will play a role. But similarly, if I have a very stiff spring, this means I have a high vibrational term, which means I am not going to want to stretch out. So this will dampen any sort of effect. So larger rotational constant, more likely I am to have this distortion. Larger vibrational constant, less likely I am to have this distortion. So it is worth noting that our vibrational constants are actually going to play a significant role when trying to analyze some of our rotational spectroscopy. And again, this is going to be tend to be more dominant for high rotational energy levels. At low rotational energy levels, this should be a fairly small effect, but still can be non-negligible. So next time, we're going to be finishing up our discussion of rotational spectroscopy by really diving into this idea of of having a coupled effect in between uh, rotational and vibrational spectroscopy. Until then, take care.